So it's my pleasure to introduce our speaker of the day, Riedl from University. So he will talk about Geometric Lang-Vojta Conjecture for hypersurface of degree 2n EPN.
I want to thank the organizers for the invitation to speak. I'm very excited to be here, and my flight got in a little late last night, so if I look a little extra tired, that's why. But I'm glad to be here. I'm glad to be talking about something that I really enjoy talking about, which is hyperbolicity. So this is a conference with two people from at least two different angles on geometry, like symplectic geometry and algebraic geometry. I'm very much in the algebraic geometry camp, but especially if you're not in the algebraic geometry camp, please ask lots of questions. I've tried to make it accessible and easy, but it's hard with someone from a different field. So if I get questions, I'll make it easier for me to aim it in a more understandable to everyone direction. So the type of thing I study are conjectures motivated by sort of by number theory, but also by complex geometry and curvature. And the basic idea is you want to understand, based on the canonical bundle of the variety, you want to understand what does the geometry look like. And so I want to talk about for this case, I'm going to be talking about the general type range. Let me do the curves example. Try and motivate. So first of all, I'm working over the complex numbers for the whole talk. And in case I forget, X will be a smooth projective variety, unless I say otherwise. But you should, whenever you see me write a variety, it's going to be a smooth complex variety. So let's think about curves. We've got we can think about, well, what is the curve? What is its genus? What is its universal cover? And what are the non-constant holomorphic maps from C? Well, so the first curve I want to start with is P1, just the Riemann sphere. This is a curve of genus 0. The universal cover is P1 itself. And there are lots of non-constant holomorphic maps from C, right? You just remove any single point from your Riemann sphere, and then by stereographic projection, the rest of the Riemann sphere is isomorphic to the complex numbers. And so you have lots of non-constant holomorphic maps from C. But let's do another curve. Let's do an elliptic curve. These have genus 1. The universal cover is the complex numbers themselves, right? Elliptic curves are just the complex numbers mod out by some lattice. And there are also lots of non-constant holomorphic maps from C, like, for example, the universal cover or any translate of it.
Does it make sense to say there's less somehow?
I feel it like in my soul, but I don't have a precise way. I don't off the top of my head have a precise way to say why it would be less.
Finite dimensional family, or am I getting it wrong?
I don't think, I mean, because any entire function on C you just compose with the map to the elliptic curve.
Oh, I see. C to C and then project.
Yeah.
So
So that gives you
a lot.
it's a lot. Yeah.
From C, yeah, okay.
Then let's take a curve of genus at least 2. For these curves, the universal cover is the disk, and there are no non-constant holomorphic maps from C, right? Because if you had a map from C to the curve, it would lift to the universal cover, and there are no bounded entire functions except for the constant ones. And so we see a dichotomy here, right? And let's also get up the degree of the canonical bundle of C. Remember, the canonical bundle is the top exterior power of the cotangent bundle. And so that's a line bundle on a curve. The degree of it is 2g minus 2. So for a P1, the degree is -2. For an elliptic curve, the degree is 0. And for a higher genus curve, it's it's 2g minus 2, which is positive. And so the goal is this negative, the 0, and the positive, that should govern all sorts of properties of the geometry of the varieties. It should govern the rational points on these varieties. It should govern the curvature properties. It should govern the homomorphic maps from C, and it should govern other things too. And there's this family of conjectures that make this precise. There's a conjecture that I'm not going to talk about today called Mannon's conjecture, or geometric Mannon's conjecture. That's for Fano varieties, and it's a precise way of saying there should be lots of rational curves, rational points, homomorphic maps from C, like lots of them. And there's like a precise sense in which there should be lots. What I'm going to talk about today is this case, the positive case. And it's called, there are various versions of it. It's called either the Lang conjecture or Lang-Vojta or Green-Griffiths Lang conjecture. And I'll go through more. But the goal is to make this, make sense of this for higher dimensional varieties. Make a conjecture and then start testing cases of the conjecture. Right, so the right on the board what I just said, we should say, what should this look like? For dimension bigger than 1. All right, well, let's get some definitions for the types of objects I'm considering. Here, I'm talking about non-constant holomorphic maps from C. I'm going to call those entire curves. So an entire curve is a non-constant holomorphic map from C to a variety X. And so the basic conjecture is that if the canonical bundle is positive, there should not be very many entire curves. So the conjecture, this version of the conjecture is usually called the Green-Griffiths Lang conjecture. So suppose X is smooth. Before I forget, this is joint with, I'll mention a couple things, but the main result I'm going to talk about is joint with Chen and Wern Yeong. So suppose X is smooth projective. And the canonical bundle is positive. So KX, the technical term is big, but you should think, if you're not familiar with big, it just means KX is an ample line bundle. There are, like, as you take tensor powers of it, you get lots and lots of algebraic sections. Then what we'd like to say is, hey, there are no non-constant homomorphic maps from C. That can't possibly be true for higher dimensional varieties, right? Like, suppose let's take some variety X, and then let's blow it up at a point, right? So we have our X, and then we have the blow up, which is some exceptional divisor E.
You use the orange, yes.
Orange, excellent.
Orange, yes, it's really best. Well, especially for the recording.
So we blew it up and we get some exceptional divisor E, which is isomorphic to some projective space. And so even if blowing up does not impact whether KX is big or not. If you started out big, you blow it up, you're still going to be big. And so Pn-1, of course, has lots of rational curves and lots of entire curves too, right? Like it has lots, like all the lines in Pn-1 are P1s. And so those all have tons of entire curves. And so even if we started with something that had no entire curves, we blew it up, and then suddenly we have lots of entire curves. So there's no hope that we would get no entire curves on every variety of general type. The best we can hope for is that the entire curves are like contained in some proper subvariety, and that's indeed what we say. So there exists some proper subvariety S in X. Containing, or when I say subvariety, I mean an algebraic subset. It could be a union of several. But it contains the images of all entire curves. Right, and so the general picture we have, this was the example picture. The general picture we have is very similar though. We have our S, it's of general type, which should say something about the curvature, and it means that there's some bad subset S where there could be lots of entire curves. And then outside of S, there are no entire curves. And that's the conjecture. This conjecture is very much open, and it's open for even many familiar varieties. I'm going to go through. So, I mean, it's also an extremely well-studied, big motivating conjecture in this area of hyperbolicity and complex geometry. So I can't just like talk about all the work on this conjecture because we'd be here all day. So I'm going to give you a very high level overview, and I'm going to focus on my favorite example, which is the case of hypersurfaces in projective space, and tell you more about the work that's been done on those.
So is it the case that in general your subvariety will be of codimension one?
No, well, I mean,
Somehow.
no, there's no particular reason to expect that. Like there are examples of hypersurfaces. Well, I mean, you could always take the subvariety to be codimensional.
Because it is the same statement.
Yeah. So there's
Well,
no, I don't think it's expected that they will be codimension one, and like that the entire curves will sweep out something of codimension one. It could be, yeah. So little is like officially proven. I don't know that there's like a proof of this result, but there's some evidence that suggests that it's not
Take
that.
a given variety, and then you pick the given variety and cut it. That triangle, so that contain the elliptic curve. So
I see. Yeah, that's an example. In abelian varieties is like one of the very few. I won't talk very much about this, but abelian varieties are one of the few like subvarieties of abelian varieties. This conjecture is roughly known. But I mean by work of Liu, lots of people, Yamanoi, Liu, a long list of names, but and so like Stephen was said, if you take a subvariety of an abelian variety with an elliptic curve in it, the elliptic curve will have lots of non-constant homomorphic images of C. Take some hypersurface that contains it. That hypersurface section will contain the elliptic curve, but will generally contain no other torus translates, and is known for subvarieties of abelian varieties. It's just the torus translates, like that. Which is that was a really long way of saying no, it doesn't have to be codimensional.
But here you assume the H is big. You cannot take abelian varieties.
Yeah, I'm taking a subvariety. So you take an abelian variety and take some hyperplane, like hypersurface section, and then it'll be big. Yeah. But for subvarieties of abelian varieties of general type, the result is known. The conjecture is roughly known.
I see.
What about for surfaces?
It's very open. Yeah. I mean,
Complex variety.
yeah. I mean, like forget surface. So for hypersurfaces in P3, it's open.
I see. I was thinking if it's elliptic, I mean, you're in a surface, elliptic surface, and that's got lots of torus fibers, so that would have lots of cut.
Yeah, exactly. So an elliptic surface cannot be of general type then,
Right.
because like for exactly that reason, then it's swept out by the holomorphic images of C.
Right.
Yeah, exactly. So the varieties we're interested in are ones that cannot be like that. Right, a couple related definitions. We say X is Brody hyperbolic. Brody hyperbolic if it admits no entire curves. Right, and so we're gonna need this definition in a second. If we take a hypersurface in Pn, which is, I want to make this like the motivating example of the talk. A very general degree D hypersurface. Right, so what do I mean by very general? I mean outside, like you've got a moduli space of hypersurfaces and it's outside a union of countably many components, which if you like in layman's terms, it means just like take a random number generator and use that to generate the coefficients of your polynomial. And that's a very general form. And so if you take a very general degree D hypersurface, then the canonical bundle, I mean, this is for any hypersurface, the canonical bundle will be d minus n minus 1 times h. And so you can see this will be big if and only if d is at least n plus 2. Right? For large d, this will be very positive and lots of sections. For small d, this will be negative with no sections. So the conjecture for these hypersurfaces, this is called the Kobayashi conjecture. Is that if d is at least 2n minus 1, then x is hyperbolic. Right, and so this is it's stronger than the Green-Griffiths-Lang conjecture in that it's saying it's hyperbolic on the nose, but it's weaker because it's saying like, hey, just being big isn't enough to be hyperbolic. Or I mean, it's not weaker. It's the conclusion is stronger and the hypothesis is stronger. Is what I'm trying to say. Right, we're saying D has to be larger than just the minimum to make it general type.
And hyperbolic here, there's no relation to the use of hyperbolic in hyperbolic geometry, for example.
No, a very close relation. So like Brody's theorem is that if you're Brody hyperbolic in this sense, then there's then the Kobayashi metric is non-degenerate.
I see.
So it's like I mean there's like some subtleties about like you have to be compact for them to be equivalent, but this definition I'm giving is equivalent to Kobayashi hyperbolic.
Yeah, okay.
Is that what hyperbolic you were asking about?
Well, I don't exactly know what Kobayashi hyperbolic is, but there's a standard metric that on this thing that would
Yeah, the Kobayashi pseudometric. Yeah. And you are hyperbolic if the Kobayashi pseudometric is non-degenerate. And Brody's theorem is that if you're a compact complex variety and you're Brody hyperbolic, then the Kobayashi pseudometric.
Okay.
Yeah. So this is the one from.
It is related to.
Yeah. It's almost exactly the same thing with a couple like technical caveats.
Okay.
This has been worked on. The Kobayashi conjecture has been worked on by a ton of people, including Hsu. I'm just going to say the names. There are just too many to write down. Hsu, Demailly, Brodbeck, Deng, DeVario, Merca, Rousseau, myself and David Yeong showed that the Green-Griffiths-Lang conjecture implies the Kobayashi conjecture with the optimal bound. And then Bercy and Kerwin and Ta. But what the result is that if D is much, much larger than N, like some polynomial in N, then you could get the Kobayashi conjecture. So if you get it, but with not the optimal bound. So you can see there's progress on hyperbolicity, but studying hyperbolicity is hard. Like even for this very natural example of hypersurfaces, we're not very close to like testing the boundary, right? In order to test a conjecture like Green-Griffiths-Lang, usually if Kx is like really, really huge, it's easier. When you have a lot of positivity of the canonical bundle, it's easy. You have more to work with and it's easier to study. If you want to say like, hey, Kx being big is really the crucial thing, you need to test right up against the boundary when Kx flips from being big to not big. And at that, like on the boundary, and so the boundary cases of these theorems are usually the hardest ones. And on the boundary, it's too hard, like the Brody hyperbolicity, it's just too hard to check. So Demailly has a proposal. So in general, not always, but in this subject, the algebraic geometry is usually easier. So Demailly made a new definition about hyperbolic. He said X is algebraically hyperbolic. If there exists just some choice of ample divisor, an epsilon positive, such that for all curves E and X, 2G minus 2 is at least epsilon times C dot H. The definition is of algebraically hyperbolic. And what it's saying is, hey, if you have a curve that has large degree, the genus must be large.
Could you just read what is written there?
Yeah, X is algebraically hyperbolic if there exists some ample H and epsilon greater than 0, such that for all curves C and X, 2G minus 2 is at least epsilon times the degree of C. H degree of C.
So H is an hypersurface?
Yeah, exactly, right. I'm working with projective variety, so I'm saying just like H is not so important what H is. It means just you need some H in order to talk about the degree of the curve. So I'm saying embed everything in some projective space. And then I'm saying if the degree of the curve is large in this projective space, then the genus must also be large.
Sorry,
Yeah,
when you wrote about the degree D hypersurfaces there,
yeah.
that's just introduced the conjecture of Kobayashi, right? It's not an example of a hyperbolic.
Correct. It's not an example of a hyperbolic thing. It's an example of a variety for which we might consider the Green-Griffiths-Lang conjecture, and then also the Kobayashi conjecture. Any other questions?
Why is there a 2n minus 1 in Kobayashi conjecture?
Yeah, it's because of lines. Well, so I think it was done if you look at surfaces in P3. So n equals 3, and so general type in P3 is 5, D equals 5. And so if definitely you have if there's going to be any hope for it to be true, it has to be true for surfaces. And so quintic surfaces are the first ones you could like K3 surfaces are not general type and they're known to contain lots of rational curves. So quintic surfaces is the first one where this could be true. So that's the -1, and then you could ask, what about the 2n? And that's because if you look at hypersurfaces of degree 2n minus 3, they always contain lines, like the general one does. And so if you contain a line, you're toast with respect to being hyperbolic. And so it's like the boundary is 2n minus 2. I'm actually going in that direction in just a second, like to talk about exactly because I think the edge cases of this are really interesting. Any other questions before I do that? Great. So we're talking about algebraically hyperbolic, and I said this is a way to try and get a handle on which things are hyperbolic. We can check which ones are algebraically hyperbolic. And so Demailly proved that hyperbolic implies algebraically hyperbolic. And then he also conjectured the reverse implication, although that's not known. And so algebraically hyperbolic is a weaker notion than Brody hyperbolic. And so if you want to figure out when there's something's Brody hyperbolic and we're trying to get a handle on this conjecture and we're trying to test the edge cases, we should figure out what's algebraically hyperbolic and use that to as evidence for the conjecture. Like if the algebraically hyperbolic ones line up with the conjecture, that helps us know what we think should be true. And that's what I want to talk about. So going to your question, right? You said for hypersurfaces, why did we expect these things to be? I don't know. This much of this work postdates Kobayashi. So this is I think Kobayashi's reasoning is just what I told you. But then this is more evidence that he got it roughly right. Maybe off by 1. Is what we do know for hypersurfaces. So I'm writing a huge list of names of many people who worked on this this problem. And so Yeong, she's my collaborator, but not for this. This was an independent project. She was my grad student. So Clemens, Ein, Wazan, Pacienza, Josh Good, and myself, Yeong, and Abe. And so the result is if X in Pn is degree D and very general, then X is algebraically hyperbolic if D is at least 2n minus 1 and n is at least 3. So I'm gonna write the name of the person to get the last sharp bound. So Clemens and Ein did preliminary work that started the story. Wazan sort of improved their bound by 1. Pacienza improved it by 1 more in large dimensions. Josh Good and I did it in lower dimensions. And Yeong also did that. So the edge case here, the last case was just gonna do myself, the quintics in P3, that like filling in that last case. So this was like in the 80s and the early to mid 90s. And so like and this was in 2019. So like it's fairly recent still, that like filling in the last case for D at least 2n minus 1. But the theorem is yes, it is algebraically hyperbolic. And then for D at least 2n minus 2, Pacienza got most of them for like large n, but the last case, or the second to last case, I should say, was Yeong. And that was last year, I think. But recently. And
P5.
yeah, so it's an octic in P5. And so there's one open case, right? So if n equals 4, that's open, it would be probably expected to be algebraically hyperbolic, but it's not known. If n equals 3, then we're in this case, they're not hyperbolic. And so
I have a question. There's
Yeah.
one with D equals 2n minus 2 and n equals 3, which fails this.
what?
So there's one with D.
Yeah. If n equals 3, then D is 4, and these are quartic surfaces in P3. These are K3 surfaces, which are not general type, and they're known to have lots of rational curves.
And with n equals 2, we can just use the discussion at the beginning and.
Yeah, exactly. N equals 2 is curves, so it's so those are well understood. Like which ones, like a smooth curve. I mean, you just use the genus formula. So that's for algebraically hyperbolic, and then we can also think about the Green-Griffiths-Lang conjecture, right? About like, can we find an exceptional set and say you're algebraically hyperbolic outside that exceptional set? And we, there's been work on this as well. Here it doesn't. I think some of the results are only for like large enough n, and I did not write it down quite carefully enough with that. But I just want to give you a flavor of the type of result. So we say x is algebraically hyperbolic outside the locus of lines if D is at least 3n plus 1 over 2. And x is algebraically hyperbolic outside. Actually, I'm going to just write approximately. I don't swear by this plus 1. It could be plus 2 or plus 3. But x is algebraically hyperbolic outside the locus of lines and conics if D is at least like 7n over 5, something like that, and n is large enough. That was Abe's result, and that's from I think this, I forget when it appeared, but this year or maybe last year. So very recent. And the picture you should have is, hey, lines and conics, these are rational curves. So definitely you can't be, that has to be in your exceptional set. It's saying like, okay, so you've got some lines, that's part of your exceptional set. Maybe you've got some conics. Okay, that's part of your exceptional set. And then outside of this, you're algebraically hyperbolic.
When you say outside of that, couldn't you have a curve which is not one of these lines or conics, but just intersects them?
Yes, yeah, those curves exist, and we're saying those curves have to satisfy the 2g minus 2 at least epsilon.
Oh, so when you say outside, you mean that they're not entirely contained?
Correct.
Entirely.
Correct. Exactly.
They
that is
could,
what I mean.
they could intersect.
Yeah. There will be curves that do intersect, and they all satisfy the bound.
Right.
You know some example when the two definitions
Coincide?
Yeah.
I mean, so for the Kobayashi conjecture, that's known for D very large. And then also this is.
I mean, when the Brody hyperbolicity is the same of the Maillet hyperbolic.
Yeah, I mean, so we know examples where both are known to be true.
Okay.
Right, like as soon as you prove something is Brody hyperbolic, then it's known by DMIE that it has to also be algebraically hyperbolic. And so anything that you know to be Brody hyperbolic will have the definitions coincide. But it's not, I mean, I think that's not what you were asking. That's like, it's like, that's a literal answer to your question, but that's like, it's for the wrong reason. We like checked Brody hyperbolicity. As soon as you check Brody hyperbolicity, then you know it's both.
But if you don't know Brody hyperbolicity, so if we start by check the my hyperbolicity,
Yeah,
is there some example when you can make some computation?
I don't know. I don't think I know. I mean, so abelian like subvarieties of abelian varieties will have that property. Like by this translates of torus thing. I think that's it. I don't know, Stephen, do you know any?
Don't worry about it. So we can continue.
Yeah. I don't know any.
What about this very general? Is that part of Kobayashi's thing or
That's part of Kobayashi's conjecture. Yeah.
very general?
Yeah. There's the general versus very general. I don't swear exactly which one he wrote in his paper, but the solution was for very general and everyone was very happy with. I mean, we would love to get general instead, but everyone was very happy at the time with very general, and it was published in a very nice journal. You need some sort of generality because you can always find a hypersurface that contains a line of like even an arbitrarily high degree. So you can't be hyperbolic in that case. So that's the case for that's roughly what's known for compact hypersurfaces. You can also ask the same question, especially this hyperbolicity question for the complex. Right, this is like going off of what Carl's talk this morning said. If you want to study the complement of a variety in like something that's not compact, in algebraic geometry, it's usually better to take a compact variety and remove a compact divisor and then study the complement. That's usually easier than just like studying something that's not compact. It's knowing what your compactification is makes things easier. And that's what we do for complements of hypersurfaces. So I need to set up a couple definitions.
So just a remark.
Yeah.
So in order to prove the other implications, so algebraically, hyperbolic implies hyperbolic.
Yeah.
So you could of course get that implication if you prove that the theorem that Clemens and this theorem is sharp. That is, you have the converse, let's say. But this is no. But if you had the converse, then you would have. Then,
Oh,
then you would then if you had converse, then you would have a high degree, and then by the if it is true.
Yeah.
So then you would have hyperbolic.
Yeah. Then you would have the optimal bound in the Kobayashi conjecture. Yeah.
So would it be the scheme of the proof of this implication?
What would be
The scheme for this implication from algebraic, yes.
we
you're
don't.
saying? How does one prove this?
Yes.
I have no idea. I would be very I would have
Because
very proud of my paper.
Now or we don't have any scheme.
Okay.
Yeah, I agree. I think it's lots of people would love to solve it, but I don't think we're at the level of like, oh yeah, someone's gonna work it out in 5 or 10 years. I mean, someone might, but it's because they had some idea that none of the rest of us know. So we're talking about complements. And so we have a related conjecture, the Green-Griffiths line conjecture for complements. And it's saying if D in Y is a smooth divisor with KY plus D
Okay. It could
big,
it's two.
then Y minus D union then I have to tell you what S is. Then there exists some S proper subvariety such that Y minus D union S is hyperbolic. So this is saying, hey, like for a complement, like so here we have our Y. And then we have some complement, some divisor D that we're taking out, and we're saying, hey, there could be some entire curves contained in the complement of D let's let S be the union of all those entire curves. And we're saying the union of all those entire curves is some proper subvariety. And outside of that subvariety, there are no entire curves inside Y that don't meet D. Here we truly here it's not like outside in that previous sense. Here we mean outside in the sense that the entire curve does not meet Y. That does not meet D. This conjecture was also extremely well has also been extremely well studied. Even for the case of Y equals P2 and X is a smooth plane, a general, like a plane curve, sometimes smooth plane curves. Often it's easier if you take lots of components to your divisor, and so that's also been really well studied. Let me just write some names. So for hypersurfaces, Green did it for I think 4 components, but maybe it was 5. There's Death Loft. Whoops, that's 1 L. Schumacher and Wong and Babette and Siu and Yeong. Whoops, Yeong has a U. And Brodbeck Dang. And the result of David Yang and myself that shows Green-Griffiths Lang implies Kobayashi conjecture that also applies in the complements case. And but the result is that if D is much greater than N, then Pn minus some very general hypersurface is hyperbolic. But again, we still have we're not testing the boundary case here. And so I want to make an analogous definition to algebraic hyperbolicity for complements. And it's mostly what you'd expect, but it's a little subtle to set up. So we say that YD is algebraically hyperbolic outside of some set S in Y if there exists an ample divisor and epsilon positive such that for all curves C in Y but not totally contained in D union S, we have the inequality, and it's almost the same as before, but it's 2G minus 2 plus I of CD is at least epsilon times H dot C. And what is this I of CD? This is the number of points of intersection of C and D. Right, the way to motivate this definition here, this 2G minus 2, this is the Euler characteristic or negative Euler characteristic of C. It's roughly the Euler characteristic, the topological Euler characteristic. And so here, when we have if we have a curve C, which maybe will be orange, and it meets our D, we want to think, well, what is C? What does that mean, like in the complement of D and Y? And it's well, we remove these points, and then we have a curve in the complement. And the number of points we remove, each one gets added to the Euler characteristic, or subtracted from the Euler characteristic, I should say. And so this number is also the negative Euler characteristic. And so we're saying, well, Euler characteristic has to be large. Let's. I'm gonna boil it down to one really specific question. Any questions about the abstract thing before we we focus it into one specific question about plane curves? All right, well, so this conjecture is the result that I want to highlight in my talk. And so let me precisely state the algebraic hyperbolicity conjecture for complements, which is often called geometric Lang-Vojta, and I think that's mostly because, I'll mention that in a second. It's mostly just in terms of who worked on it in which order. I don't. So the geometric Lang-Vojta conjecture says that if D is a divisor in Y, with KY plus D big, then there exists some proper subvariety S of Y such that Y comma D is algebraically hyperbolic outside S. And then so for hypersurfaces, we have Chen, and then set using a different technique, Pacienza and Rousseau both proved that for D at least n-1, X Pn is algebraically hyperbolic. Right, and so here they're proving geometric Lang-Vojta, and they're also proving that this exceptional set S is empty. Right, so this is the analog of the hypersurfaces case. I mean, in some sense, this is complements of hypersurfaces, and the result is better. It's like exactly known when the complement is algebraically hyperbolic. Like by this result. Right, so Zeidenberg.
Confused. What's this pair XPN?
XPN is projective space, Pn,
Right.
and then X is a very general hypersurface of degree D.
Oh, so X is contained in PN.
X is contained in Pn, right? This is the log version of this conjecture, right? When we talk about a pair being algebraically hyperbolic, we're thinking about Y minus D being algebraically hyperbolic.
Yeah, you've written it in the other order here. Yes.
Oh, sorry.
PNX. I mean,
It should have been Pnx. Thank you.
that might make a bit more sense.
Yes. I think I order them interchangeably, so catch me and I can get next time.
Well, normally one puts the big one first. That's
Yeah.
right.
I believe you. I agree. Any other questions? All right. So then, I claimed but didn't prove that this is the sharp result if we want the exceptional set to be empty. And so the boundary case, like the frontier of our knowledge, is X and Pn of degree 2n. Very general. And so Zeidenberg had, like before, I think Chen and was the best you could do if you have empty exceptional set, because there are lines. He showed that there are lines that meet X in 2 points. So Zeidenberg said for D at most 2n, there exist lines that meet X in 2 points. And so that means S can't be empty, right? S has to contain the set of lines meeting X twice. And there are two ways to think about or see that result. The first one is just straight from the definition, right? If you have a line that's genus 0, no, right here, this definition, a line is genus 0, so this is -2. Then if it only meets it twice, this side is 0. 0 cannot possibly be bigger than a positive number. Here. So that's one way to see it. The other way is just the hyperbolicity way, right? A line is a P1, it's a rational curve. So you take a P1 and you remove the 2 points of the bound, like of D that it hits, like the 2 points of the hypersurface that it hits, and you have a like C minus the origin, which is the image of all the exponential map, is the image of a holomorphic map from C. So so this is the exceptional case. So let's think about the simplest open example then. So n equals 2, this is a quartic plane curve. Right, so you take P2 and you write down a random curve of degree 4. And we want to know, is the complement hyperbolic or algebraically hyperbolic? And so green and maybe I should have mentioned these results earlier when we were talking about other results, but these were specifically for quartic plane curves, like complements of quartic plane curves, and they had for at least 3 components. Right, the type that they use sort of like analytic techniques, like something like Nevin-Lena theory, where it's better when you have more components.
At least 3 components.
The quartic curve. So it's no longer for these results. It's not very general. You don't take like a smooth quartic curve. You take like a conic unit 2 lines or 4 lines in P2.
Right.
And you show that the complement of that is algebraically hyperbolic outside some exceptional settings.
A very silly question. You're saying the boundary case is when degree is 2n.
Yes.
But then your conjecture is when d is bigger than or equal to 2n minus 1. So I'm very confused.
No, so big, right? So like for let's work out the bounds, right? Ky here, when y is Pn, ky is negative n minus 1. And d is like d times the hyperplane class. And so ky plus d is d minus n minus 1. So when I said boundary case, I mean the boundary of what's known and not known, not the boundary of like the boundary of the actual conjecture is d equals n minus 2, n plus or whatever it is. D equals n plus 2, whatever makes this a positive number.
So the boundary is not that's
it's like the frontier is maybe
frontier of what's known.
Maybe,
So
yeah,
that's
maybe.
this is what's known. This is
Yeah.
the most. So there's you still want to go down 1 more degree. Right?
Yeah.
1 more d. Right.
And so look, this is quartic plane curve, and what I'm trying, people like studied quartic plane curves, not like they would like to study general ones, but the techniques that had been used were not amenable to it. Chen's degeneration technique also was not amenable to this, right? He would be, and it's because we know that there are lines meeting it twice, right? If you have a quartic plane curve, you will always have finitely many bitangent lines, like lines that are tangent in 2 points. Like a line should meet a quartic in 4 points, but at a tangent point, it'll meet with multiplicity 2. And so if you have 2 tangents, you can see it'll meet in only 2 points. So that has to be in your exceptional set. Another example is if you take a flex line, right? Like I'm teaching Calc 1 right now, so I'm about to teach them about flex points. That's another type, like it meets here with multiplicity 3, and then here with multiplicity 1. So that's like, again, a line that meets in 2 points. So we know that there are these like curves in the exceptional set. And we like to say like, either these are the only curves or like find some finite list of curves such that this is the exceptional set. Right, but just to like re-emphasize, suppose we have some other curve, like some blue curve here. We're saying either the blue curve has high genus, or it's contained in the exceptional set, or it meets D in a lot of points. That's the conjecture. That's what it says. And the higher the degree of the blue curve, the higher either the genus or the number of points it meets it. That's B. And so we're able to resolve this. So theorem. We say if x in Pn is degree 2n and very general, there exists some exceptional set S in Pn such that the pair Pn comma x is algebraically hyperbolic. outside S. And then furthermore, in the case n equals 2, which was sort of the most famous of the cases, like had been most like Green's paper was from the 80s. Corvaya and Zani had a sequence of like 2 papers in the early 2000s. And so people have been thinking about quartic curves for a long time. And so we also spent a little extra energy on n equals 2. Then we can show that for all curves in P2 that are not in the union of the bitangents and flex lines, (2g minus 2 plus I of C D is at least 1/2 times the degree of C. Right, so we show that the exceptional set S is the minimum possible we knew it could be. Like it's just the union of the bitangents and the flex lines. We get an explicit constant for our epsilon, 1/2. And this 1/2 is the best possible. Right. So the example 1/2 is the best possible. So there exists a conic that meets a general quartic curve in 3 points. So meeting x in 3 points. To go through why you would expect, I mean, we proved that this is the case, but let's go through why you would expect this to be the case. Right, we have our quartic curve. You'd expect a conic to meet our quartic curve in 8 points. There's a 5-dimensional family of conics in P2. So each time you like cut the dimension by 1, you can make 2 of the points come together. And so you like subtract off a distinct meeting point. And so instead of 8 points, it meets in 3 points. And you can show that indeed that happens. So there's a conic meeting x in 3 points. Let's work out what 2g minus 2 plus I is for this one. 2g minus 2 plus I. And we're trying to compare it to 1/2 times the degree. Well, 2g minus 2, that's negative. The genus is 0 for a conic. And the number of points is 3. And we're trying to compare this to 1/2 times the degree, which is 2. And so this is 1 and this is 1. And so this inequality is sharp. Are there any questions about the result?
Yes, I have.
Yeah.
Maybe an absurd question. Could you have a result of the kind of if x is in Pn is of large degree 2n, then there exists S inside x. There is S inside x such that it is hyperbolic.
Yeah.
Could you get something?
The way that I've set this up, you don't need like that. You don't need to worry about such S. We're only worried about curves that are in the complement. So we're only worried about curves that meet the complement of x. For S contained inside x, we like that would be the same as S being the empty set. But like if you go back over to where we said, oh, I might have erased it by now. I erased the conjecture. But if you look back to where I stated the conjecture, like we're looking for curves that are not contained in S union X. But that being said, here we can't. We know though that we cannot take S to be contained inside. Like we can't take S to be the empty set because we know there have to be these lines that meet it twice.
Yes, but could you take S included in X?
No, the lines are not like these bitangent lines are not included in our curve.
Yes.
Right, they're outside of our curve, so that like S has to contain these bitangent lines.
So your theorem is relative. You cannot have a kind of absolute version of your theorem somehow.
Yeah, well, I mean, there is like an absolute version that, but it was just already known. Like the absolute, I mean, or like the absolute version, it would be like a plain quintic in P3. It would be that sort of statement. Is that what you meant by absolute version, or did you? Yeah. So, like there is an absolute version, it just was already known. That's not so.
This is a better one.
Yeah.
I do have a question.
Yeah.
Actually, I go back to the definition of the naive hyperbolic.
Yeah.
So suppose that you show that your x is hyperbolic in that sense,
Yeah.
So you found some H, some epsilon, and so on.
Yeah.
So what about other divisors? It looks like, you are looking through all possible divisors and then try to find some epsilon.
Oh, yeah, you're saying, what if I change H?
Yes.
Yeah, if you change H, then you change epsilon, but it's just up to a rescaling. So if you're algebraically hyperbolic for one particular pair.
Of course.
Yeah. And like you'd have to you could just re-embed using like 2H, so you can see that your epsilon will have to change.
Okay.
But like any two ample divisors are comparable. So it's up to changing your epsilon.
I feel better.
Yeah, excellent. I sort of swept that under the rug. Are there any other questions before? I had a couple words to say about the proof, but in 3 minutes, so I can say fewer words about the proof if there are more questions. All right, so let's say a couple words about the proof. The proof it follows in some sense. So the technique of Pacienza Rousseau was it's sort of inspired by like Ein and Voisin's technique, and we follow sort of in that vein. But there's like one key advance. Well, there are two key parts. The first part, this was known to. I'm going to explain just one part clearly rather than two parts not well. So we have we need the log tangent sheaf. So given D contained in Y, we have we have the tangent bundle of Y. And what we can do is we can map it to the normal bundle of D and D, like this O of D restricted to D. And so the way to picture it, here's our Y, here's our D. And we're saying sections of the tangent bundle of Y, they correspond to like a choice of tangent vector at each point. And at points of D, we can say, hey, does the vector point off of your divisor D? Like you can say what's the component of this vector in the normal direction to D. And so the kernel here will be the log, it's called the log tangent bundle. And it's just all the it's like vector fields on Y that are everywhere tangent. So I should not drop, like this was not a log tangent section of the log tangent sheaf. It's along D, it has to be tangent to D. And off of D, there are no restrictions. And so you can work out this bundle. There's a sequence 0, like so let's let Z be a general curve violating like the bound, the algebraic hyperbolicity bound. Then we have a sequence. We have 0 goes to the log tangent sheaf, let's call it ZB, of Z to the pullback of the log tangent sheaf of P2, this is X. And the quotient is something called the log normal sheaf. Log. And it turns out that the degree of the log, so we can work out what we can take Chen classes, right? The degree of this thing will be just H dot what was it? Sorry. It'll be YB times D minus 3. What X is your plane quartic. Sorry, I should say it. This is YB dot H. It's D minus 3, which is 1. So it's YB dot H, negative YB dot H. This is going to be, well, the tangent sheaf to B is 2 minus 2G. And then the negative log XB, it's minus the number of intersection points. And so the upshot is the degree of this log normal sheaf is 2G minus 2 plus I minus H dot Y. Whoops, I called it 1. I should have called it Z. Y is Z. What's it anywhere else? And so Pacienza and Rousseau did this, and sort of if you reinterpret what they did, they gave a lower bound on this degree, which gives a lower bound on 2G minus 2 plus I. But they, what you still need to do is you need to say, hey, you need a better lower bound. But that only works if your curve is not one of the bitangent lines. And so what we do is we look at the pullback of this syzygy bundle M1, right, which is defined by the sequence 0 goes to M1, goes to O cubed, goes to O of 1, goes to 0. And so you pull back M1, if M1 and through some general construction, which I can explain after the talk, you get a dominant map from this M1 to the log normal sheaf. And so if this M1 is stable, like it's slope stable, it's a bundle on a curve. If it's slope stable, then you get the right bound on the degree of this, and then you get the results. And if it's not slope stable, then you sort of turn the crank and go through this construction. You can show that to each point of your Z, like here's our Y, and then we've got some exceptional curve Z. And we're saying to each point of Z, we're associating a line corresponding to the like destabilizing kernel here. And so, and then you can work with those lines, and you have to do a lot of work, but you can show that the curve ZB, the lines of ZB intersect D with fixed modulus, and like it's a fixed configuration of points. And so that gives you like very explicit information about what your curve ZB can be. And then you study it further and show that the only ones that violate the bound are bitangent flux lines. Thank you.
Questions?
That's a very naive question.
Yeah.
Where does the notation log comes from?
Log.
Why do you use?
why-
Why do you use the word log?
It's called logarithmic, and it's for like log derivative, right? So like you want like the it's for the cotangent bundle, so if you're taking like OY of log D, like you want like suppose Y in a local chart is given by like in a local patch, your coordinates are like x1 up through xn. Then the sections of omega y is generated by dx1 up through dxn. And the sections, and suppose D is like the vanishing of like x1. Let's choose coordinates where D is the vanishing of x1.
Sorry, it's the vanishing up.
Yeah, D, like our divisor D, yeah, is given by x1 equals to 0. Yeah, exactly. Then this in local coordinates is given by dx1 over x1. X2,
And then
xn, and this is the logarithmic derivative, like it's the derivative of the log of x1.
yeah, oh yeah, sure. It's the main, it's the best definition also to was the Fubini study called symplectic form exactly in this way.
Yeah. So it's log, and then the log tangent sheaf I gave is just the dual of this,
Of course.
and that's where it logged. So the term log, but like even this morning when we were talking about log pairs, and it's all from this. It's when you want to study the complement, you use this type of cotangent sheaf.
I should ask the question this morning.
Yeah, but this is it. It's the same. It's the same.
Other questions?
Yeah, so everything here is an algebraic category, of course.
Yeah.
Integrable and everything. So then you can of course make sense of these definitions if you replace a complex structure by an almost complex structure. For instance, you have geomorphic copies of C inside your manifold.
Yeah.
And I do remember, say, I think 20 years ago, there was someone who gave a talk in Toronto about possible connection of these hyperbolicity notions with Floer homology. And I was just wondering if you knew any development in that.
I do not. Wait, do you know who gave the talk?
Laure Biolay. She's French.
B-I-A-L-I.
It's a French woman. It's Anne-Laure.
Laure Biolay.
Yes, it's
Biolly. Yeah.
No, I don't know. I mean, which it doesn't even mean it didn't work. It just means I happen not to know if the results.
So you're not aware.
I'm not aware of it.
Any possible connection.
Yeah. I mean, although I think that would be really cool.
Well, if not, but thank the speaker. There's a wine and cheese. Just the next speaker first.